So hello, everybody. Thank you for being here today. In this presentation, I want to talk about simulation, but not simulation in the way that we use to simulate our RTL or HDL models. In this talk, I want to show you how we can use FPGAs in order to simulate hardware circuits. Hardware circuits like power supplies or essentially any other circuit that can be represented, can be implemented using mathematical equations. So we are talking about maths. First of all, let me introduce myself. My name is Pablo. I came from Spain, from Valencia, and I am, as most of us, FPGA designer. I like to bring FPGAs to places where they are not used to be used. This is not the case of this conference, but for example, I have been talking about FPGAs at cybersecurity conferences. I also write on internet. You can read me on LinkedIn X, Hackster, Hackaday, and especially on my blog, controlpaths.com. If you want to reach me, you can reach me on X and also on my email. So imagine that you want to implement a control algorithm with to control a power supply. A power supply will be, for example, a power state of several kilowatts or even several megawatts. In order to perform that simulation, you would need, in the first place, the control platform. The control platform will be based on a MCU. Also, you will have some memory in order to store your algorithm and some kind of communication in order to communicate with the external world. In addition, we're going to need power supplies in order to supply that microcontroller, memories, and communication. Some acquisition system in order to obtain the measurements from the power states and make it available to the MCU. And we also are going to need gate drivers in order to be able to manage the different switches of the power states. In addition, we're going to need the power states. Since we are talking about high power devices, we are going to need something that can manage high voltages. So we are going to need high voltage DC link and then the power states. With these two elements, we will have the product we are going to sell. We have the controller and something to control. However, if we want to test this in different scenarios in order, for example, to make it compliant with several certifications, we're going to need anything else. In this case, we're going to need a test bench. The test bench will be based on the device under test, which is our unit, the unit that we want to control, and also we're going to need another test unit. This test unit will be also a high power unit. It has to be able to manage high voltage with a high voltage DC link and also a power state. The test unit has to be at least, has to be able to manage the same power than the device under test and even more power in order to be able to generate different kind of fails, for example. In addition to the test bench and the control platform, we will need to take measurements from that, from the test, from the even the device under test and the test unit. So we're going to need high voltage instrumentation in order to take measurement from high current, voltage, and high power. This will work, and it is still working today in many different companies. However, it is a little bit dangerous because here you will have a real power, real voltages which are moving within the test bench. So this problem is, as I said, it's not a new problem, and the industry has some fixes for that. For example, hardware in the loop. If we are working with hardware in the loop, we will have the same control platform that we are using in our final product, but we are going to replace all the test benches for a model of the power state. And also, since we are working in a mathematical model of the power state, we don't need another power state, another model of the power states. For example, if this power state is a solar inverter, if we want to recreate, we want to simulate the grid conditions, that grid condition can be represented just with a sinusoidal wave. In addition, since hardware in the loop target uses low voltage has 10 volts or 15 volts, we don't need high voltage instrumentation. We're going to be able to take all the measurement just using low voltage instrumentation, like the typical proofs we have in our system. But we can go one step forward. These targets are usually based on FPGAs. So if we have an FPGA and we have the power stage, the model of the power stage, and also all the scenarios, all the simulation environment, we can integrate inside the virtual instrumentation. Virtual instrumentation is just we are going to take the different measurements from the model, and then we are going to need in a way in order to extract from the FPGA that measurement. Also, we can integrate in this highly integrated hardware in the loop the acquisition, because the acquisition in the control platform will be based on filters, and filters can be represented with mathematical equations. So I just need to integrate that mathematical equations inside of the hardware in the loop. And the same for gate drivers. Is there are no switches that we are going to move, or high power switches that we are going to move, we can integrate this also in the gate driver. In this case, the control platform will be reduced just to the controller, the MCU, power, memory, and communication. In this talk, I want to focus on the power state model because for me it's the most interesting part. Okay, imagine that you want to control a back-boost converter. Back-boost converter is it's the diagram you have here, and it is based on two different switches, an inductor, capacitor, and also a load resistor or any other kind of resistor. We're going to need also the input voltage. In order to obtain the model of this circuit, and essentially of any circuit, we're going to need to know the mathematical equation that describes the behavior of that circuit. In this case, there are two elements that can be so a little bit complex, such as the inductor and the capacitor, because they have what is called a state. An inductor, the equation that represents the behavior of the inductor is this integral you have here. The inductor is, in this case, is a current control voltage source, which is represented by the integral. The same for the capacitor. Here you can see that the capacitor, the behavior or the current through the capacitor is a function that depends on the derivative of the voltage that we are going to apply. Then these two switches are being represented using a nonlinear equation. This is the equation that you have here, and finally the voltage of the load is the same as the voltage of the capacitor. So if we want to implement this into the FPGA, we are going to need to translate all these equations into some synthesizable code. And it is very easy because I know that FPGAs cannot do integrals, or they cannot do derivatives. But an integral is essentially an addition, a derivative is essentially a subtraction, and this is a multiplexer. So we can translate this diagram into this diagram. Here you can see these two multiplexers that represents the nonlinear equations of the two switches. Then we have this block, the block of your left, which is the inductor. The inductor has a voltage applied to the inductor as an input, and then it will return us the current through the inductor. It is the same for the capacitor. In the last slide, I showed you the capacitor as a derivative, but we can invert that, make that the opposite, and translate it into an integral, which is essentially what I did here. You have as an input the current through the capacitor, and then we are going to obtain the voltage in the capacitor, which is the same than the voltage on the resistor. And then here you have the model of the resistor, which is essentially the Ohm's law that returns us the current through the resistor. We can go one step forward. I mean, we can, if we need a more realistic model of the power converter, we can replace some of our some of our components to a more realistic models. For example, usually the inductors are represented with a series resistor. We can add this here. And the same for the capacitor. The capacitor, or a more realistic model of the capacitor, will be the one which have a series resistor, an ESR on the capacitor. So we can add these two elements, this new resistor, to our model. And we will have this. You can see that the model of the inductor is have the resistor in series with the inductor in the top side. And also for the model of the capacitor, you have the resistor. And it is very interesting to analyze a circuit like this, because here you can see that the series resistor of the inductor is represented as a negative feedback, which makes the systems more stable. And this is essentially what the resistor does. It is just the opposite than the resistor in series with the capacitor, which is represented as a positive feed-forward. So this kind of circuits make the systems more unstable, and this is exactly what the resistor will do. The rest of the model is the same. We have again here the resistor model, which is the Ohm's law. In order to implement this in an FPGA, we will have something like this. We will need something that will control the execution of the model, and also we're going to need some kind of communication in order to modify the values of the resistor or the capacitor. So in case that we are using an FPGA, we could have a UART configuration and a simulation control. Then we're going to have the model itself, and finally we're going to need something that will adapt the values of the model to the gain of the DAC, or the way in which we're going to extract the values of the model. So in this case, we have a gain control and a DAC driver. If we are using an SoC, like a Sync or a PolarFire SoC, we can replace some of these blocks. For example, we will have a hard CPU or a soft CPU, and then either the simulation control and the model will be managed by an AXI wrapper. The gain control and the DAC will remain, because we are going to we still need to extract the measurements to our control platform. Okay, I want to show you some examples of these models working. In this case, we have the Board RT35T, which is based on an AMD RTX 7. And here you will see the backboost model, a level 1 backboost model running at 60 nanoseconds. In this case, the analog output I use is a 12-bit 100 kilosamples per second. In your left, you can see the output voltage of the state, which since the backboost is an inverter converter, you can see that the output voltage is negative, and it has the typical ripple we can find in this kind of converters. In the other side, we have the inductor current, which is also a triangular wave, and in the top of the second capture, we can see the input voltage, which has to be a square wave. In this case, it's not a perfect square wave, not because of the model, but because of the analog output I am using. In terms of utilization, it's important to know that these kind of models are just very low code. So the utilization will remain very, very low. For example, in the case of the backboost model in the RTX 7 35T, the utilization is around 5%. The same for the DSPs used is 13%. This amount of DSPs used, it depends of the accuracy of the model we're going to need, and if we are optimizing or not the use of the DSP. But it can be as less as 1 or 2, depending on the accuracy we need. Since we are working with just very low code, we can migrate the code that it is running in the RTX 7 to, for example, PolarFire SoC. In this case, I have no captures of this, but there's a boost model level 1 running at 40 nanoseconds, again with the same analog output module. And the last example I want to show you is this, which I use the repeated STEMLab 12510. It is based on an SoC, and what makes special this simulation is that the analog output in this case is 10-bit 125 megasamples per second. This speed will allow us to see some of the effects that we cannot see if we are using a slower ADC, a lower DAC. Here again, you can see the ripple in the current of the inductor, and now we can see that the voltage of the inductor is a square wave. You don't need to see the ripple because the ripple is not in the model, it's in the proofs I use. And in the other side, we can see an an open loop response of the model. And here you can see two more output with the typical ripple that we can find of this kind of model, this kind of devices. And that's all I want to tell you. Thank you very much. I will be around, and you can find me on GitHub, X, and controlpaths.com. Thank you very much.